an indicator is a weak acid, so let's call it HA. So it has the usual weak acid ionization equilibrium. And the thing that makes it special is that the colour of the protonated form is different from the colour of the deprotonated form. So if you take a familiar example like methyl orange, which you used in the first year when we did some titrations, this form is red and this form is yellow. Now this is actually quite a common thing with organic acids, because if they're coloured at all, it usually means they have a delocalized pi system. You need delocalization of pi electrons basically to bring the energy levels of the ground state and excited state close enough together that they absorb in the visible. And if you think about pi systems, if you think about just a very simple one like this, you know that if it has an amine group attached to it, for example, that lone pair will become delocalized into the ring. But of course, if that becomes protonated and uses that lone pair to form that, then it's obviously no longer available to be delocalized into the ring. So it changes the pi electron distribution in the ring, and that will change the energy required to excite those to an excited state, and that will change the colour. So it's not weird that indicators should change colour, because it's kind of what you expect to happen if you have a delocalized pi system like that. So we can see why an indicator would change colour just by thinking about Le Chatelier, because he says that if we have a low pH, that corresponds to a high concentration of H+, this equilibrium will shift to the left to oppose the change. So if we have a high concentration of H+, the yellow A- will tend to get converted into the red HA, and so we'll see red. Conversely, if you go to high pH where H+ concentration is very low, this equilibrium will shift this way to oppose the change, and so red HA gets converted into yellow A-. And of course at some point in between you're going to get a situation where both of these forms are significantly populated, and then you get a mixture of red and yellow, and as you will remember from primary school, if you mix red and yellow you see orange. So that's the sort of qualitative principle, but we can also think about that in a quantitative way using the Ka. So if we write Ka is equal to H+ times A- over HA, okay, standard Ka definition, we can rearrange that in a helpful way if we just divide both sides by the H+ concentration. So we get Ka over H+ is equal to A- over HA. So if we're interested in this point at which the indicator is just on the point of changing colour, because obviously that's the colour that you're going to be interested in when you're doing a titration, is that midpoint when it goes from red through orange. When does it reach that orange point before it goes on to yellow? So if we're interested in that, effectively what we're saying is that we're interested in the point when these two concentrations are about the same. Right, because if you've got equal concentrations of red and yellow, then, you know, to a first approximation you're going to think, well, that's going to look orange. And if these two concentrations are the same, that must mean these two numbers are the same, because obviously if these two are the same, this side equals 1, so that side has to equal 1. And so we can make the statement that Ka is equal to H+ when A- is equal to HA, which is when the colour changes. So that's very interesting, because what it tells you is that the pH at which the colour changes will be equal to the pKa, because if we just take minus log of each side, we can get that pKa of the indicator is equal to the pH of the colour change. Now, in fact, of course, it won't just change instantly, because you're going to see a change over a sort of range of concentrations, because obviously it doesn't just switch from red to orange, it'll go from red through sort of reddish orange and then yellowish orange and then yellow. But as a rough guideline, we can say that if you have more than sort of say 10 times as much red as yellow, then basically you're just going to see red. And if there's more than 10 times as much yellow as red, you're just going to see yellow. And that corresponds to being 1 pH unit either side of the pKa. Okay, and you can, if you play with the equation, you can convince yourself that that's true. But basically, the colour change occurs over a range of about 1 pH unit either side of the pKa. So that obviously has implications for using the indicator in a titration. And since we're using the indicator supposedly to tell us when the situation is neutral, you would hope that the pKa of the indicator would be around 7, so that the colour change would occur maybe 1 pH unit either side of the neutral point. And so it may come as something of a shock that the pKa of methyl orange is about 3.5. So this is one of these moments when you might start to, question everything in life, because you've confidently believed all this time that when you used methyl orange in a titration, it told you when the solution became neutral, but actually it told you when the solution reached a pH of around 3.5. And so you think, what's this all about? Why do we even bother then if it doesn't tell us when it's neutral? But what we then have to do is think about those titration curves that you've been learning about. So here's the sort of curve that we got for a strong acid being titrated with a strong alkali. So for example, if we had HCl in the conical flask and we gradually added sodium hydroxide to it, we would get that sort of curve. So remember, you get this near vertical region with pH 7, the neutral point that we're looking for, somewhere in the middle of that vertical region. And what we're interested in finding is the volume at which that happens. So in other words, what we're aiming to achieve when we do a titration followed by an indicator or followed by this method or whatever is the volume. Okay, so that's the neutralization volume, or the equivalence point, if you like. So what we've now learnt, shockingly, is that methyl orange doesn't tell us that. Methyl orange tells us what the volume is when the pH reaches somewhere around 3.5. So if we mark 3.5 on here, it's going to come somewhere there. And now hopefully you see why you get away with this. Because this region is near vertical, the volume when you reach that point where it's 3.5 and the volume where you reach that point where it's 7 is very, very similar. It's probably, in a typical titration, it's probably within a drop or two of reaching this point and reaching this point, because the pH is changing so steeply around the equivalence point. You get away with it because although the indicator actually tells you when it's pH 3.5, that's incredibly close in volume to when it's pH 7. So actually, if you have an indicator with a pKa anywhere in the range from sort of around there up to around here, you get almost the same result. Actually, if you do a very careful titration with methyl orange and then with phenolphthalein, which has a pKa up here, you can see the difference, because it's not completely vertical here. It's got a slight slope to it, but it is very, very small, and so you get a very good approximation using that. So you need to be able to explain that, why you get away with using an indicator with a pH range which is quite far away from neutral, so long as the pH range comes within the vertical sort of region of the curve, then it's fine. So you could sort of mark on the pH range kind of like that and say, yeah, you know, that's within the vertical part of the curve more or less. I mean, we may be slightly outside it at the beginning, but pretty much it's within the vertical part of the curve. And that will have two important features. The first is that the colour will change very abruptly. Okay, because you can see within a drop or two, you know, a very tiny volume change here corresponding to a drop or two being added, you're going to go from this pH to this pH, so go from red to yellow. So very abrupt pH change results from that range being within the vertical region. And secondly, and importantly, that volume where it happens is very close to the volume where it's neutral, and so it does give you a good indication of what you actually want to find out, which is the true equivalence point. So now let's think about what happens if we do an experiment with a weak acid and a strong base. Okay, so remember, that's the sort of curve you get when you have a weak acid titrated with a strong base, that you still get a vertical region, but it only really is in the basic part of the curve above pH 7. Below pH 7 you see this rather gradual change reflecting the buffering that happens when you have the mixture of the weak acid and the conjugate base. So if we then think about what's going to happen if we put methyl orange in there and try to follow a titration, so we can mark on that range again, you know, a little bit either side of pH 3.5. So, you know, our range is going to be something like that. And you can see now that we have a massive problem, because first of all, the colour is going to have changed well before we reach the equivalence point, because this is the equivalence point. Okay, but the colour's already changed. You know, it starts changing as we start adding volume. It's going to start changing at this point. Okay, so this is going to be the start of the colour change. And it's going to finish changing when we reach about here. So that's the end of the colour change. And you can see it's completed its change long before we reach the end point. So that's the first thing that's very different from what happened with the strong acid, that it this time doesn't give you at all a good estimate of what the true equivalence point is. It massively underestimates it. But secondly, you're going to know there's something wrong because it doesn't change abruptly. Because you can see, instead of occurring in a couple of drops, which it would do if you were within the vertical region, to complete the colour change, you're going to have to add this huge volume to go all the way from there to there. So it's going to change colour very gradually over a big volume range. So it's completely useless for finding the end point for both those reasons. You don't get a sharp colour change, and it's in the wrong place anyway. So that means you have to be really careful when you're choosing indicators if you don't have a strong acid and a strong base. And if your situation, as in this case, is that you have a weak acid, you can see that ideally what you want is an indicator which changes colour in that sort of range there where it's vertical. Because if you do that, then it is going to give you a good indication of when you reach pH 7, because that volume where that happens is very close to the volume where you are at pH 7, and it's going to occur abruptly. Because you're in the vertical region, a couple of drops is going to take you from one end of the colour change to the other. So what you're ideally looking for is an indicator with a pH range somewhere up here. And there are such indicators. So phenolphthalein is one, which is a widely used indicator, and that would give you a great result, because it's not affected by this sort of slow change in pH that happens down here, because it only changes when we get into the basic part of the curve. So it's horses for courses. You have to choose an indicator to suit the titration curve that you're going to get. So phenolphthalein is fine for a weak acid and a strong base. It would also be fine, of course, for a strong acid and a strong base, because it's going to be within the vertical region still. But what about if we have a weak base and a strong acid? Okay, so this one, remember, is the sort of curve that you get when the acid is strong, so you get a nice vertical region in the acid part of the curve. But once you get above around pH 7, you start to get the buffering effect, and so the pH changes now much more gradually, and you get curvature straight away, no vertical region really to speak of above pH 7, and the limiting pH is not nearly as high. So let's see what would happen if we used our phenolphthalein in this situation. So again, if we mark on the phenolphthalein range, it's going to be sort of about here. And you can see the problem, that by the time the phenolphthalein starts to change colour, we're already past the end point, because this is going to be where the start of the colour change occurs at the beginning of that band, and you've already missed the end point. And again, it's not going to change abruptly, it's going to change over a range, and it's only really going to be complete by the time you get all the way up there. So it's the mirror image of the problem we had with methyl orange. Methyl orange was fine up here because it was vertical, but it had the same kind of problem in the low pH region. If we do this now with methyl orange, and we mark the methyl orange range on, it's going from sort of there to there, and you can see it's fine. It's within the vertical region, so you're going to get a faithful approximation to the true neutralization point. So again, what we come down to is that you have to make sure that the pH range of the indicator comes within the vertical part of the curve, and if it does, you get an abrupt change, and that volume where that occurs is very close to the true equivalence volume. And in an exam they will always tell you what the pH range of an indicator is, so it's very easy to apply that rule. So finally, let's look at the situation where both the acid and the base are weak. Okay, so that's the sort of curve you get when both the acid that you're starting with and the base that you're adding to it are weak. That this time you don't get a vertical region at all, because all the time there's this buffering going on, and so you get these kind of more gradual changes. And what that means is that it doesn't matter what indicator you choose, you're never going to get one that will give you an abrupt pH change. And so, you know, basically indicators are going to be useless for this titration, whatever indicator you choose. So if we used phenolphthalein with its range up here, then you can see the problem is that we've missed the end point by the time the colour change starts to occur, and then it occurs very gradually over this broad range of volume rather than occurring within a drop or two. If we tried methyl orange instead, which would be sort of down here somewhere, then it's the opposite situation, that it starts changing much too soon, long before we reach the equivalence point, and again it changes very gradually, not abruptly. Even if we did, you know, there are indicators available with a pKa of around 7, but it's not going to change abruptly, so it's going to be very difficult to use an indicator. So basically in that situation you have to use another method like this, actually monitoring the pH, to try to find your best approximation to the equivalence point.